Well, today I'm joined by Dr. Jeff Gillow of Arcadis to discuss our recent groundwater monitoring and remediation column, Emerging Opportunities for Beneficial Recovery of Critical Minerals from Metals Impacted Waters During Remediation. Jeff, thanks for joining.
Yeah, thanks, Greg. Thanks for the opportunity.
Your interest in critical minerals recovery, what's generated that? And maybe in your response, you can also provide a little bit more definition on what we mean by that term, critical minerals.
Yeah, sure. I think critical minerals it's a term that a lot of people have been hearing in the media and in the scientific technical literature lately. It's the realization that in order for us to advance the technologies that are bringing clean energy, advanced computing power, and essentially just improving people's lives, those technologies are going to require critical mineral raw materials. And essentially, those are metals, mostly metals. We know about copper and the need for copper and electrification, and lithium for battery technologies. But there's a whole host of other metals people may not be as familiar with. And the challenge right now is all of the estimates say that we just don't have the supply that we're going to need for the next 50 years to achieve all the things we want to do as a society. Rare earths are actually a subset of the critical minerals. So critical minerals, like I said, in the US, encompasses 50 elements on the periodic table, mostly metals. Graphite is one of the critical minerals, barite and fluorspar, but the others are metals. And in the paper, we actually provide some convenient ways to think about critical minerals by grouping them into their technology applications. So there are the battery metals like lithium, cobalt, manganese, nickel. There are the semiconductor metals, gallium, germanium, indium, tellurium. There are the advanced material metals, steel strengtheners. And then there are the rare earth elements, and that's essentially the lanthanides on the periodic table, as well as scandium and yttrium. So those are the traditional forms of the rare earth elements. Their properties are very unique in that most of them are trivalent cations. So they carry a +3 charge. They do tend to hydrolyze in water, which means they're not typically very soluble at neutral pH, but they do undergo complexation with organic ligands and other ligands, including sulfate and other inorganic ligands. We've learned a lot about the rare earths through mineral processing and metallurgy, so we know how to extract them from ore, and we know how to purify them and separate them. A lot of that relies on solvent extraction with organic ligands. In groundwater systems, they're typically going to be more soluble in acid environments, so acid rock drainage that you might see in mine-influenced waters due to pyrite oxidation and sulfuric acid generation. If there are rare earths in the host ore, you'll see those dissolve in that environment, but you could also have an environment that's affected by the low pH. And if you've got rare earths present, they will dissolve. So one of the easy ways of recovering rare earth elements is through pH manipulation. So actually raising the pH and dropping them out as a precipitate. But we're also learning new ways to recover rare earths through experience with these mine-influenced waters and groundwater systems. And so we're still learning a lot about their environmental behavior. It's not as well understood as compared to the behavior in a mineral processing environment. So there's a lot of effort currently to look for critical minerals. And again, various countries have lists of critical minerals that they have identified as critical for supply chains. And in the US, the United States Geological Survey publishes a list. Currently, it includes 50 essentially elements on the periodic table. There's only a handful of actual minerals, but the term critical minerals has been widely accepted as applicable to these elements that we need for advanced technologies. So what we're really talking about is finding other sources than primary ore sources. So we're looking at unconventional sources, secondary sources, and within the realm of groundwater remediation, there are actually opportunities to recover some of these trace elements that may be present in groundwater systems, but may concentrate through the process of remediation. And where our paper discusses opportunities for groundwater practitioners to take a look at this and possibly contribute to the supply chain.
Yeah, thank you. This is quite exciting. The drivers are developing, and there's some new drivers with regard to demand. And then, of course, on the recovery side, technology is evolving, making recovery potentially more economic in some situations. Maybe you could talk a little bit about how you could assess the potential for recovery. Does it make sense in a given situation? How do we evaluate the potential, the risks, the upsides? What are frameworks that we can use to look to identify potentially promising opportunities?
The paper discusses some current present day examples of recovery. So there's a significant discussion of rare earth elements in mine influenced waters. And that is the one place that there's been quite a bit of work done to actually take these ideas and implement them. So rare earth elements are needed for advanced magnet technologies, sensor technologies, and there are not many primary ore sources. Certainly, there's some sources outside of the US, and we do need a domestic supply of rare earths. So the paper discusses that and then uses some of the examples from mine influenced waters to guide groundwater practitioners into exactly how to do these kinds of evaluations. So the first thing is to think about the metal constituents that may be treated. So you may be treating copper, nickel, zinc, chromium, etc., concentrating those in a treatment system, in an above ground treatment system as water treatment residuals. So one of the things to do is to take a look at your treatment residuals and determine if those could be sent off to a refinery or a smelter, and you can actually recover the value associated with those metals that may be being treated as the primary contaminants of concern. But oftentimes, when you've got metals in groundwater systems, and a lot of times those systems may be acidic, low pH systems, there may be other trace elements that you're not aware of because they're not regulated, but they may be co-occurring with those primary metal constituents. So some of them may be rare earths. Some of them may be things like gallium, germanium, indium, tellurium that we don't have MCLs. We don't have federal drinking water limits for a lot of these constituents. And they're likely present at very low concentrations, but they have significant value. So if you're concentrating them, even though you might have parts per billion concentrations of these in a groundwater system that's pumping at a relatively high rate, you can actually start to accumulate those, and then that may be value in those residuals. So it's really thinking about what you're treating, how you're recovering those, thinking about what other trace elements may be present, doing the analysis to identify those other trace elements, and then doing a techno-economic analysis. So what are we recovering? What might the value be? And then perhaps how can we recover some of these other trace elements more efficiently and more effectively? So thinking about bolting on other treatment technologies to enhance recovery of, say, rare earth elements that have significant value.
As we move forward, what are some of the key research or demonstration needs you see for this to become more widely adopted and become part of the standard consideration for remediation systems?
So the paper goes into a variety of modalities for treating groundwater, and the two major approaches include ex situ and in situ treatment. So in ex situ treatment, which would be typically a pump and treat system with an above ground treatment train, thinking about how to augment those treatment trains with selective recovery technologies. So you can be targeting maybe through ion exchange or pH manipulation or a membrane technology. You can actually be selectively concentrating individual trace elements that might be present in a groundwater system. Because you're exactly right. If we start to think about these treatment strategies or these treatment requirements as a means of developing a resource and perhaps returning some value on that investment with respect to treatment, that can be really beneficial from multiple angles. So research needs include what technologies are most amenable to combining together to target individual critical minerals. So that would be on the ex situ treatment train. And in situ offers a significant number of opportunities. So we think about permeable reactive barriers. Can we make those modular so that once you have a media that might accumulate your primary target constituent, that could be zinc, it could be nickel, it could be copper, and also some trace elements. Again, all of those are critical minerals. Can we remove the module, ship that off to a refinery, and then replenish the media. So in the paper, we talk about the horizontal reactive treatment well and the opportunities that affords, because you can place these wells in a groundwater plume. They are installed parallel to groundwater flow, and they actually enable flow focusing through the well. That well can be filled with treatment media. We can fill the well with, say, zero valent iron or an absorptive media or an ion exchange media, such that over time we'll be accumulating those critical minerals, and then those can be recovered later on. Now, there are great analogs in natural systems for accumulation of low concentrations of constituents from groundwater systems. Ionic clays in China are enriched in rare earths because they're highly reactive towards very low concentrations of rare earths that flow through these clays in groundwater systems. We also know that uranium roll-front deposits, reducing zones that accumulate uranium, and that uranium is coming in at very low concentrations. So the HRX wells could actually be placed and left in place for 6 months, a year, a few years, and then recover. The media can be recovered, and you can realize the potential related to the accumulation of those trace elements. So again, I think in terms of research, it's really thinking about the science and engineering around ex situ and in situ treatment systems and being more intentional with respect to recovery of these trace elements that may be critical minerals in these groundwater systems.
Jeff, thank you so much for your time today and your support of this column. It's been a pleasure speaking with you.
Thanks, Greg. Appreciate it.